First of all, I'd just like to thank everyone for taking time out of your day. I know you're all very busy, and we appreciate that. And I want to thank the Valmont guys for coming out all the way from Nebraska and put this on and kind of educate us. We're calling this the 2014 AASHTO workshop. So, first of all, is to kind of update you on the code changes, even those that haven't been implemented yet here, right? But we're adopted here, I should say. But it's always good to keep in the know about what's out there and what's probably coming our way, that sort of thing. So, and then here I'll turn it over to Ryan. Just a quick introduction of who we've got here. Everybody knows Debbie, right? Debbie, and then Dave Kellogg is our Vice President of Sales. And Greg back there manning the camera does our marketing and that sort of thing. And then, of course, Steve Barrett's in sales, and he kind of handles the north. And I'm Scott Jackson. I run the southern operation for MH, and I'm also heading up a new venture for us called Roadway. We're calling it a Roadway division. We kind of decided that with the advent of LED and all that it entails, that it was time to maybe expand on the great job that Debbie's been doing and Steve's been doing in the north, and really better infiltrate the small towns, the municipalities, get more into the lighting side of the roadway again, which we used to do, but kind of, got out of for a while. And now we've got a lot of neat tools on the lighting side and certainly on the control side that we're going to be talking more and more about. So I just wanted to let you know that that's a new MH entity that we'll be promoting, and so when you see it, you'll kind of know what that's all about. So with that, Ryan, I guess I'll let you take it from here and educate us. Let me know how you like the lighting once we get going, because I can make it better on the screen probably.
Awesome. I'd like to add my welcome. It's great to have everybody here. We're happy to come out and spend some time with you anytime we get the opportunity. Debbie asked me to mention we're recording the presentation today, so if there's people in your teams that couldn't be here, we'll edit things down and we'll make that available to you after the fact. Additionally, we talked about getting the presentation out to you as well with contact information for Steve and Zach and myself. So we'll absolutely do that when we're done today. Okay? Another housekeeping item. As we move through the presentation today, feel free to ask questions as they come up. We don't need to hold questions until later in the presentation. When it comes up, just ask them. We'll kind of mingle around the room, and if you need us to raise hands for you, we can certainly do that too. Okay? Again, welcome, thank you. You guys' time is awfully valuable, so spending the morning here is taking you away from your work, and we might very much appreciate that. Introductions for MH. The one thing that I will add, Valmont isn't who we are without our agent partners, and MH is certainly the cream of the crop for Valmont. So you guys are quite fortunate, if you ask me, to have these people that you're working with every day. So thank you guys for your efforts very much on our behalf. Always like to give just a brief overview on who Valmont is. Some of you may know Valmont. People have been at Valmont 18 or 20 years ago, seen some of our facilities. But today, Valmont comprises 100 facilities globally and roughly 10,000 global employees. The business units that we are prominent in, lighting and traffic, which is what we'll talk about today. Some of you may know about our utility, our transmission distribution businesses. Valmont Newmark is a primary brand name in that space. Irrigation as well. You guys see center pivot irrigation systems here in Colorado, just like we do in Nebraska. That's actually the roots of Valmont's businesses in agriculture. And then finally, coating, pipes, and tubing. We are one of the largest, if not the largest, coatings providers globally. Just a little bit about Zach and Steve's sort of team. I'll introduce them specifically in a moment, but Valmont thinks of ourselves as a company of engineers. So whether it's in the lighting and traffic space, whether it's in our application engineering, research and development, product development, our machine builders business, we are engineers in every facet of the business. So we're probably not as per capita in your businesses as you are with the number of engineers, but relative to our competitors, Valmont certainly is a leader with engineering aptitude. A little bit of introduction about the two guys that are going to spend the most time talking today. Zach Thiemann, first of all, professional engineer. He manages the United States application engineering team. One of the guys that works for him is Steve. He's also got Barry Slottick, who you guys have worked with in the past, and Nizam Qasim that handles another part of the territory. A little bit about Zach. He graduated from the University of Nebraska at Lincoln, did his postgraduate work at Iowa State, and is continuing his education still today. Been with Valmont 5 years in a number of different roles, always in leadership capacity. Zach spent a lot of time in R&D where he was the lead on our FHWA breakaway, decorative basic and breakaway applications. Did a wonderful job with that several years ago. Spent some time in our communications businesses, monopoles, lattice towers and the like, and then most recently back in the lighting and traffic business. Owns a number of state stamps as a professional engineer. And then Steve Osborne. Steve is the guy that's responsible for the day-to-day business in Colorado. So when you guys see drawings come back, when you guys see calculations, that's generally the output of Steve. And if Steve happens to be away, he's got guys that back him up a little bit. Steve really owns Colorado. So we'll get you contact information if you don't have it, and you guys get to know Steve a little bit better moving forward. But actually, that's not right. Steve's background, I'm sorry, Steve. Steve graduated from the University of Colorado Boulder. So that's a real slight against Steve, and I didn't do that on purpose. I apologize. The other thing I'll point out, he's wearing a red shirt today. I know that's not easy for you. Steve's professional career spent several years, 4 years actually, at Texas DOT down in North Texas. Has still a lot of friends down there and a lot of professional relationships that he draws on still today. Spent 15 years in consulting engineering, and that was in Omaha area, right? Has been with Valmont now 9 years, and we're very pleased to have him as part of the team. You can see he owns a number of state stamps as well.
Except for Colorado.
Yeah. We're working on that.
We're working on that right now. Okay. That's really what I had for introductory. Any questions before we turn it over to these two guys? Thank you.
Can I just give you a quick overview of what we're going to go through today? We're going to start off with an AASHTO 2013 overview, the changes mainly from 2009 to 2013. If you go through there, any questions, make sure to ask them. Then after that, we'll go into more of a design comparison. Steve grabbed some of the traffic, some high mast, and a camera pole that was utilized here in the state of Colorado. Show you how that would change from the current 2009 if we were to switch to 2013, what the implications would be, just to kind of show more of an example. Then there's a little presentation on vibration, fatigue issues, LED effects on structures, kind of what's changing in the industry there. Do an overview of product development, some of Valmont's capabilities, and the big one there too is our H-Law, our welding process we've adopted, implemented and you guys adopted about 2 or 3 years ago, kind of what that is, how that works, so you guys got some insight on that. And then we'll finish up the presentation with kind of a peek into the next AASHTO code that was just adopted in June at the Subcommittee of Bridge Structures road publication next year. So we have a draft copy, so we'll go through some of that, kind of show you some of the changes. It's ASD to LRFD, so there's going to be some unique things. Start out with the standard disclaimer. The stuff we put in here, we've copied some stuff out of the AASHTO code, so want to make sure they get their mentioned. And then some of the presentations, we've worked with others in the industry. So some of the stuff you might have seen other places, maybe others have the same figures as us. So don't want to come across this as all 100% all Valmont created, but we work with the industry quite a bit, and so there could be some other references used. All right, AASHTO 2013 overview. Before we go into it, how many people here have had a chance to look at the AASHTO 2013, have an understanding of what's in that, the LTS 6? Anybody? All right, good. So we all know what AASHTO means. The AASHTO is this is the 6th edition of the code. It's LTS 6. same nomenclature as 2009 LTS5, and so on. We'll kind of go through by section changes. Mainly, you're going to see all the changes in chapter sections 5 and 11. So, sections 1 through 4, there was no significant changes that really affect sizing of the structure, design, or things that we found important. So, we skipped through that. We get right into section 5. Some of the background on AASHTO 2013, what I've learned reading through it and talking with others is it was very much, it seemed to be a kind of a research-based code. A lot of research out of Lehigh, Purdue, in regards to NCHRP reports, stuff they did in the lab, turned into stuff in the code. So sometimes you'll see some effects from the code that might not, as designers, as people using it day to day, don't necessarily jive with what we see in the field. Yeah.
What about the research that Carl Frank did down at Boston?
Yeah, there's some of that went into it, but the two big reports were the two NCHRP reports, Rob Connors out of Purdue and Sagata Roy out of Lehigh. And so Dr. Frank was involved with that, but not, his wasn't as prominent. Definitely was involved. Was there some research in particular you're thinking
Got
of?
incorporated in that, they used his work.
He was, in particular, I know Lehigh Group kind of used him as consulting, and there was some back and forth, but the lead research was through Dr. Roy with Lehigh.
Right, but I mean, they took his results, he did a lot of testing.
Through that
Right,
lab,
lab.
through the NCHRP study there through Lehigh.
That got incorporated, as I'm saying, this research.
Yep. So, kind of kick it off, one of the changes to the AASHTO code is they incorporated a minimum number of sides of tubes. So depending on your tube diameter, you had to have a minimum number of sides. So anything less than 13 inches, you had to have at least an 8-sided structure. Round is considered infinite, so it would fall within any of this. But what that was doing was really taking away, your square poles, 6-sided poles, all the sharp bend radiuses that could have stress risers or will have stress risers and create concerns and issues on the fatigue side. So you can see they have a chart, and there's the equation in there also. So under 13 inches, you have 8 sides minimum. From 13 to 28 is 12-sided minimum, and then over 28 is 16-sided minimum. Then also, going back to stress risers and concentrations in the corners, they have a minimum bend radius, either 1 inch or 5 times the material thickness. That way you weren't getting too sharp coming around and attracting that stress right there. And sometimes you might have a little bit of a welding issue, so trying to keep those hot spots away. Moving on to the next portion of this section, 514.3, they adopted a transverse plate thickness minimum requirement. In 2009, the requirement was that your base plate thickness had to be at least as thick as your ankles. Instead of just doing it that way, this time they said you have to have a base plate at least 1.5 inches thick if your shaft diameter is less than 8, or if it's greater than 8 inches, 2-inch thick base plate across the board. That's if you're designed to section 11, which is fatigue. So if you have fatigue design, you had to have, for most structures, or over 8 inches, that's most of them, you have to have at least a 2-inch base plate. So you go back to some of the previous ones, and I guess people show you that in the design comparisons, how they'll increase some of the base plate thickness just because of this. Yeah.
So you said 514.2 pretty much eliminates square holes?
If you were designing it to AASHTO, it's the AASHTO code, you're not going to be able to meet it according to how the code is laid out right now. Throughout this, if you look at the opportunities and if you've had issues, if there's concerns as we're all engineers, you can take an exception to something and we can work with it. But according to what they found in the research, they said we want to eliminate that in the AASHTO designs. Big thing I just want to reiterate again, the minimum base plate thicknesses is only for fatigue designed structures. So your common light poles down the side of the roadway, 35, 40 feet tall, that doesn't require this minimum thickness because those are exempt from fatigue designs. Through the research, they also found that there can be issues with the welds, either a combination between welds on the top of the backup ring. Sometimes the lower quality welds were placed in there because they were just using more seal welds to keep the galvanizing out. But the base plate shaft connection is your primary area for fatigue, not failures. So any sort of improper weld, lower quality, could attract the stress in there, start creating a crack on top of the ring and actually crack through the shaft. So combination of two things they did. One is they have new requirements for vacuum rings when you do or don't place a weld at the top, how you determine fatigue stresses. And the number two thing they did was depending on when you're putting depending on when you're welding it, depending on how tall the backup ring could be. And that's because of UT. When you try to UT and bounce a sound wave into the joint, if you have that weld at the top of the backup ring, sometimes you can actually get that sound to go into the backup ring. You won't be able to properly inspect your shaft to base plate weld. It's got a backup, bounce off the back of the shaft. If it catches the weld, it goes from the backup ring. So they said if you're going to weld the backup ring, you got to do it after UT. If you're not going to weld it, you can't have taller than a 2-inch tall backup ring. And here's more of that information. So when you are welding the backup ring to the top, you have minimum heights. And again, that's all based off the equation at the bottom, which tells us the minimum heights for your transducers to do UT, so you can get a proper inspection down on that joint. So you want to make sure you have a quality weld down there, or else you're going to potentially create an issue for fatigue. This is probably the section that we've seen the biggest implications of the code affecting the design since the handle rims. There's always been a check, they've had in the fatigue section to look at the stresses of the handle rim. But now they've incorporated a minimum diameter, and that's that the first bullet, it's the first sub-bullet. So this is for an unreinforced hole. If you have an unreinforced hole, your diameter of that hole cannot exceed 40% of the tube diameter. So you put a 3-inch hole, or say a 4-inch hole, into a hole, unreinforced, but it's pretty unlikely, it's round numbers. Your pole shaft has to be a 10-inch diameter. If you anything less than 10, you would violate this portion of the code. One of the things about this is one of the areas for owner approval. Specifically called out in the code, these sections, these next 3 sections I'll talk about, with owner approval, you can deviate from with sound engineering practices. But there is a requirement for 40% of the tube diameter. They also dictated the corner radiuses, because the sharper the corners, the more stress concentration you're going to pull into that corner and potentially create an issue with getting some cracking through there. So they say your corner radius has to be 30 to 50% of the width of the opening. If you want to round a corner, you don't really want a square, sharp 90-degree angles. And the third thing they put in there was the distance from any transverse plate, so like a base plate. How far from the base plate does the hole have to be a minimum? And they suggest that 1 hole diameter. So if you have a cutout 6 inches up from the base plate that's on a 12-inch hole, you actually have to move that cutout to 12 inches of clear distance. So that's from the bottom of the hole to the top of the base plate. And you move on to the next subsection of the code, and now they talk about the reinforced holes and cutouts. So now this is the ones with the handle rims, much more prevalent, larger holes we'll see in structures. They also have the 40% requirement. So really any reinforced handle rim on structure without owner approval will have to follow this 40% rule. They also have the 30 to 50% width of the opening for cutout for the corner radius. Let me clarify one thing on the first bullet. The 40% is the inside width of the rim, not the outside width, not the hole in the shaft. It's the inside opening of the rim in this situation. They also have the minimum clear distance between any hole or cutout to any transverse plate, like the base plate has to be 1 hole diameter. So we've seen some times where that's actually moved handle rims on the base of a traffic structure up because of the need to require that clear distance. And then the third thing is a suggestion. They suggest all rims on a sign and signal support structure be a minimum of 3 gauge, 0.23 inch. That's not realistic. So, and they go to a little more detail in the high mast. So they usually call out this requirement high mast. First 3 bullets are all identical. The difference is the 4th bullet you'll see at the bottom. They suggest in this situation for high mast that they recommend a minimum of 1 inch thick rim. So it's a recommendation. But when Steve goes through his example, he'll show you the effect of this. Mainly, we're seeing this first bullet, the 40% requirement, how that's affecting structures and at times dictating designs quite extensively. And but one last thing for these 3 is this is one specifically in the code. It allows owner approval, sound engineering practice to deviate from some of these requirements. Move on through section 5. They have mast arm pole connection. As everybody familiar with the wraparound gusseted or ring stiffened connection versus the old boxed with no ring stiffener on it. I think the next page gives a little bit of a view of it. Here you'll see the ring stiffened is this bottom one where you have the side gussets coming out. There's actually a ring stiffener that wraps around the pole, and that's the new connection that was really developed after a lot of the issues prior to 2001 AASHTO in Wyoming. And the old connection is this top one where there was no ring stiffener. You had the side gussets, you had the front plate. This is to connect the mast arm to a pole shaft. So in the previous codes, they'd always put provided benefit to the ring stiffened wraparound gusset style connections, that it was a higher fatigue resistance. You could put a little more stress into that and be within code. When they did all the testing in the laboratory, they found that they both had the same life cycles in the laboratory testing. So it goes against a little bit of what we'd seen in the industry that led into the 2001 code. So they say that parts are acceptable for mast arm to pole connections, and not jumping too far into chapter 11, they both have the same fatigue rating. Infinite life, you don't have to design for fatigue. So you can have either of those and meet AASHTO 2013, where in 2009 or 2001, you would be limited in your stress if you use the non-wraparound setup. Section 516, minor little change, but it's worth pointing out. The code says without order of approval, a washer should be placed between the mast arm flange and the flange plate on the pole, and that helps alleviate any sort of warping issues in that connection between those two plates, so you have a solid connection there. I know that's something that in some states, it's one you can exclude. So like some states have said we don't want that, and that's there mainly because they've seen some issues where after fabrication, plates are a little more warped than you would have with an A6, so you have some fit-up issues. It's something that good quality control hopefully would alleviate most of that, but putting a lot of weld onto a thicker plate like that, preheating it, will allow it to warp. And so this was, I see that. Yeah.
When you, I'm not a welding guy, but maybe somebody in this room is a welding guy. But from what welding I have done, you simply take another flange with a blank flange, and you bolt that blank flange out. You're welding over here, and that blank flange runs upstream to prevent the cupping that you see. As the weld cools, it won't pull, because the other flange is strong enough to hold it. You guys do that stuff?
We've done some stuff like that. So we've had a project where we were welding on a 2.5 inch thick face plates, and we were placing, I want to say it was on the thicker structures we were trying to weld, or we were welding, we were welding 2 inch thick shaft to it. So we were placing somewhere in the range of 60 welds of passes of weld. And that was one way to try to stiffen it up. You'll still get some deflection, because as soon as it's going to pull, when it's welded up there and switched up, it's going to keep it from warping it. But as soon as you take that off, take the weld off, you still have the built up stress. It's going to want it to pull open. The biggest thing we found, and I think most people that are welding do the same practice, is the preheat. Proper preheat throughout the process, getting that flange up to the proper temperatures will help alleviate that as much as possible. But putting stiffeners on there while you're welding will keep the deflection down. But you still have that stress built up within it, that as soon as you cut it off or unbolt everything, it's still going to give some. Might not be as much, but it's not a fail-safe to not have any deflection.
But the work that's been done, like at the University of Texas, quite frank, shows that you don't really need stiffeners anymore. We haven't taken ours out yet because we just haven't enough staff to work on stuff. But isn't that where it's going? When we face this issue, you're going to get rid of the stiffeners.
You're talking the stiffeners from the pull shaft to the base plate?
Yeah.
We don't suggest using those to begin with, so we don't design stiffeners on ours.
Yeah. Criminal.
So
the weld that you make, the simple weld that you make down there, that doesn't cause any cupping, right?
It does. That's what this is about. Because if you put on 6 or 7 or 8 passes there on a thick plate, you will get that stress right in the middle. It will cause warping. That's without the proper preheat. So
That's without stiffeners. It's just this.
Yeah, because we rarely put stiffeners on something designed to it.
It's a full pen backup ring. There's a lot of weld in there to get that full penetration weld in there. So it does heat up, like Zach said. It heats up a lot in that area. So by preheating the transverse plate, it kind of makes everything about the same temperature. So when it cools, it all cools together. And we do several passes where those passes, and they take a lot of care to do that. And we have met with a lot of plate warpage issue. We've taken that down substantially, and we need, in a lot of states, California had done some amounts where they have really decreased that tolerance amount. We have been able to make that work with this process that Zach was talking about.
Right. And what we've done is kind of given up. We still have the stiffeners out there, so until we take them out, we're stuck with that. We figured that's where most of the problems come from, and you're saying not necessarily. Can be done there, that weld with pipe. So what we've done is called for portable line facers to be used to true up the surface before galvanizing.
We've seen some of that. I think one of the things we're going to see less compression, our warpage now in a light structure following the thicker flange plate. Over the flange plate, you have obviously more stiffness in there, but you know, in the past, if you had a 38-inch shaft on a maybe a 1 1/4 inch flange plate, 1 1/2 inch flange plate, you're putting in there with the filler over, you put 6 or 8 passes on that. So the thinner that flange plate is going to potentially open up the opportunity for warpage. But thicker plates are going to help that out a lot too.
Okay. Proper preheat.
Proper reading is definitely it too.
And we don't want to cut that in the code, because that's a big secret, how to get all that done.
Well, we figure a lot of that should be coming from AWS. The suggestions and the requirements in there is following that through proper control.
And for what's between the plate
Yeah.
and we create a gap.
Yep. Yes.
And we want any much of it. And we can recommend you seal them.
Yeah, we've suggested silicone. We like to bring this up because we hear a lot of those concerns. We want that connection to be weather resistant, weather tight. We don't want water in there. We don't want exposed wires. And we totally understand. We've suggested some silicone in there. I think one time, somebody went with their out of like a neoprene pad fabric in there to, as a gasket to close up that gap. We're seeing more and more as we bring this up, and the entities are talking about it. That's one of the first things they'll say is, take that off. We don't want that to be part of our standard drawings or our order. And that's why we pointed out you can exclude it if that's not of interest. This might be a little bit of a eye challenge, but in this code, they provided details for the wraparound gusset and for the box gusset. We try to highlight some of the main areas of changes. One is pulling out the 2-inch thick base bolt, flange plate, and that's on the mast arm side and also on the pull side. They call it side gussets. Typical 3/8 thickness, they call it all metrics of 10 millimeter. Side gussets, they suggest not having it angle out more than 17 degrees. And they call out here that the mast arm can't exceed an angle of 25 degrees in their recommendation. So that's rise. Just quite a bit of rise, but these are the things, as I talked about, it's a testing code. A lot of the stuff they did is what they tested. They tested the setups. That's where the information comes from. They're doing a little more research, or they're discussing it. They said it comes like that. They're discussing more research on particularly the hand-forwarding issue. Now that it's been brought up more and more in the previous meetings and by a lot of the end users, that 40% rule is really dictating a lot. Steve will show you that later. So they're looking at it, getting a little more money for more research to try to alleviate and expand from 40% to maybe up to 60% of your shaft diameter. Maybe this is an area they'll do additional research into, because sometimes some of those criteria is quite large. Some of their welds they call out on a thinner shaft is 3 or 4 passes on a 7-gauge shaft is a lot of welds. So
We use a different concept. We could use any one of those that you show there. We haven't, because that's not where we went. But we don't we call the first hole down here the base section, and the end section is left on. Count that on the end section, you get rid of all of the use those details, but mount them on the end section. And I remember when we started our signal design here, Carl and Michelle objected because it caused out of line fabrication for you guys. But you've been building a lot of our signals, and you no longer have out of line fabrication. You rearrange your plan to do it. But I think that's a key element. And I talked to Roy, or Segota Roy, and he saw that too. So just a comment. Those work really great. Anything works better if it's on the inside than opposed to the base.
Okay. Additional new addition to this code is the anchor bolt connections. High masts are required to have 8 anchor bolts. In the past, you could have 4. They had recommendations of 8. Now it says required to have 8 anchor bolts on a high mast structure. They recommend 12. We're required 8.
Sorry, I missed it. What's the definition behind that structure?
High mast structure is, they call it out in Chapter 11 in particular, it's a structure over 55 feet, primarily used for lighting, lighting purposes. Over 55 feet. So stuff, you know, as you go out here, stuff along your interstates more, not so much what you see in your, in residential. The residential stuff, they'll call that low level lighting.
Like interchanges.
Interchanges, stuff that, you know, typically, I think one example we have here, the 130-foot high mast is one of the standards through Excel. So when you start getting to those size, that's some pretty big structures in 8 acres.
Yeah, the reason I'm asking, we have these 65, so what is we call a lead mast, the high mast versus
Yeah, through the code, there is no, I mean, it's low level. Actually, that's what they're call it low level, but anything that's 55 is typically called low level than high level, or high mast lighting.
Because we've got our new lowering device standard that we created for video cameras, and we've got 50s, 60s, and 70s.
And that's where it's kind of the gray area a little bit. If you consider that high mast lighting, because it's a camera, and that's kind of work with the end user on how you want to consider that structure.
Yeah, and I guess the concern of our signal in general is just the flash vibration, so you can still see it well.
Exactly.
Part of what I'm trying to figure out is there some big, like I've used some 60s before, and now I've got some 70s. Is there some big difference, or is it just a little bit bigger?
It's just a little bigger. I mean, is it talking like how those with the code would impact?
I don't know, fabrication, yeah, the code.
Oh, the fabrication side is going to be bigger, so running the fabrication is not going to be too much of an issue.
Section, not any fundamental difference in terms of what you do with it.
It would be based on your section properties for still for deflection, you know, your code stuff.
By the way, how are they vibrating? Are you able to see the ones you built?
I've heard no complaints yet. We don't have too many about yet, but I've heard no complaints. I know I was trying to watch one on top of Floyd Hill that's on a luminaire, trying to see what a VMS said about a few hundred feet away, and I just gave up because it was a windy day, and I just couldn't even read it. But
So do you think the deflection criteria is right or wrong in the code right now?
I don't know.
But
I don't know. We'll see as we have to.
the code actually doesn't have a camera deflection criteria, so it's usually user-based. What is it you guys spec out? Usually 30.
I don't know, you know, and I know our operations guy said, oh, it's 70-footer. We need to still see the camera. And I'm like, oh, it should have been done with some kind of deflection control in the design, so I think it won't be a problem, but I don't know.
A lot of what we see is a deflection. We'll see people specking out and it makes some 1 inch of deflection at 30 miles an hour, kind of operational wind speed. I think one thing we always, we'll ask questions if we see it if somebody says a 1 inch deflection of cold wind or something like that. Because now you're talking 1 inch deflection at 90 or 70, some higher wind speed.
Yeah.
Kind of the operational wind speed is where you want.
Because, I mean, we're putting some on, we put some on variable message signs, and they only go about 5 feet above the variable message sign. Operation, or maintenance guys don't like that, they get dirty, so we've now got a design that goes up 15 feet. And I asked, well, how's the deflection compare? Oh, it's still less than an inch. I was like, well, an inch and 15 feet, that's quite a deflection. I don't know what kind of limitation it was referring to, but.
So I guess we're still learning. Bottom line is we're still learning. got that button, didn't
Yeah, you created it,
you? No. All right, okay, so jury's out, we're still working.
All right. And then under the ankle bolt section, they've added in an ankle bolt retention, suggested procedure. So we get a lot of questions on how do you deal with that. We're asking advice stuff. And when you look at the history of fatigue, ankle bolts being loose is a huge issue with potential fatigue, starting to rock and everything else. So they provided this comment, or this in the commentary, an 8-step procedure, something that we provided out to maintenance or anybody doing installation on. Here's a suggestion that they have. How do you go through the turn the nut method? I throw it in now, like I said, keep talking about the deal, but is there any question right now just on section 5? We'll go into the fatigue portion. Yeah.
Been talking about the camera deflection. Is there other states or somewhere else that there is a spec that could be used so that we could not have to guess?
To my knowledge, and Steve would know this a little better, I don't think there is another state that has a standard like in their spec, but we see most commonly 1 inch at 30 miles an hour.
In several different, like Jack said, we don't really see anything that's standard, you know, but when certain state entity or city entity may purchase a certain camera type, usually there are specs that go along with that tell us what that is. Certain states have adopted, have one state that has a 0.7 at 30, 0.8 inches at 35, and 1.4 inches at 70. So I usually have to do 3 different checks and our program does follow the Petrie method for round tapered poles to check that we do a stress check and we do these 3 different checks. So it's kind of variable between different states and the type of equipment that's being used, either camera or other type of control boxes and other things that may be attached onto those poles. We implement that as part of our design and deflection process with that particular state entity.
The big thing to remember from that, those when you're speccing them, you want that deflection control to make sure that put that in the RFQ to the different manufacturers, because each might interpret the lack of a deflection requirement differently. Get very different size poles if one puts it on and one doesn't. We'll make sure you get what you want. We'll move on. Like I said, keep discussing, keep talking. I think it's great. Section 6 is aluminum section. People of background, Steve and I do field pole design for Valmont. I talked to our aluminum group up in Farmington. Their biggest thing they said that they saw in the code was the addition of a combined interaction equation for a square aluminum pole. Previous to that, there wasn't direct wording saying the square aluminum pole should be checked across the diagonals, and that's been an issue because you find that typically you're limiting direction for your capacity check. So that's something that needs to be checked, and the code specifically discusses that. Sections 7 through 10, nothing real pertinent. We looked at the concrete composite wood pole, again, coming from steel and aluminum side, didn't do as much into that. And the serviceability, which is section 10, there really is no significant changes that we saw. The big difference other than chapter 5 is section 11. That's the fatigue section. A lot of words, so I'll try to kind of summarize each one. In the past, the whole fatigue section all applied to all the different types of structures evenly. You didn't really differentiate too much other than importance factors between a high mast and a traffic structure. You might take out galloping, of course, be that vortex shedding. The vortex shedding check was the same for all structures. This code, they've separated high mast from traffic. So you have a few sections that tell you this is how you do your traffic checks, your sign and signal support checks, and this is how you, and then there's another couple sections that say this is how you do your high mast checks. Different wind maps. So in the past, there was 3 fatigue categories, 1, 2, and 3. That's the same for sign and signal support, but for high mast, there's only 2. There's a fatigue category 1, fatigue category 2. There is no more fatigue category 3. So how do you define fatigue category 1 and 2 for high mast? They determine it depends on the pole height and the distance from the roadway. Really, it comes down to if the pole were to fail, would the pole land on the roadway, or would it land still in the field and not not affect the day-to-day traffic, would it not stop traffic flow. So distance to the roadway is less than or equal to pole height, is fatigue category 1. The distance to the roadway is greater than pole height, fatigue category 2. If the distance from the roadway to the pole base is not known, we're going to go with fatigue category 1. We want to be on the safe side, but we did, figure those are going to be in intersections, in interchanges, things like that. And high likelihood you'll be close to the roadway. Like I said, they pulled the high mast lighting towers out from the traffic side, so they've actually provided a wind map in the fatigue section. So it depends on where you are in the country, it depends on your high mast lighting pressure you put on your high mast structure. So in the past it was, your natural wind gust was 5.2 psf times your importance factor. Well, now, depending on if you're a fatigue category, depending on the section, it can be anywhere from 5.8 psf upwards of 7.2 psf. So you're increasing the pressure on the high mass lighting. They've taken away vortex shedding as a separate check. They figured vortex shedding and natural wind gust is something that's really acting at the same time, so you can't differentiate the two. I'll try to talk louder, I guess they're having a party next door. And so they made it literally one check for your high mass lighting. It's all this. In Colorado, you see they have a better picture later in the presentation. Should have put it here. You see it's kind of across two different sections, the A and B. When you look at it, the big difference between A and B, if you have a T category 1, across the state it's the same wind pressure. The only difference is the wind pressure if it's a T category 2. So if it's that pole farther from the roadway, you might have a lower wind pressure if you're on the western side of the state versus eastern.
What's the little special black area there?
Tornado Alley. That's the highest wind pressure, right through the panhandle of Oklahoma, southern Kansas, you said more in Kansas, kind of right through here that's 7.2 PSF. So the old check was 5.2, now it's 7.2. The lowest wind speeds are out here, the highest wind speeds in the middle. And as you kind of look at fatigue and wind flow, open plain, you're going to have the most.
What's the source of this? Where do we get this from?
Where do you get the map?
I've seen different wind maps before on this one.
This is out of NOAA. NOAA has just a yearly mean wind velocity. This is one of the, a lot of things, I guess, this came out of one of the NCHRP studies through Purdue. Purdue did a lot of the fatigue, the high mass side of it, and this was in their report. That's based off of, I found back the section as a reference, I found the map. This just had about 20 pages of, by different cities in the different states, what is the average wind velocity for a whole year. And that's where this is coming from. And from there, the pressures. One thing that's interesting, we're in Colorado, so it doesn't affect you guys. They forgot Alaska and Hawaii.
But also on that you helped AASHTO determine on Alaska and Hawaii that you don't see on here, that you helped AASHTO to develop some code provisions within that table, and there's PB and C ranges for those two areas too. So we kind of did a little research with them on some of that.
You did that, and you got it approved in June. So next revision, so you'll see Alaska and Hawaii. We're back to 50 states again.
Okay, so I've got a project that's got like 70 footers on it.
Yeah.
I don't know whether you guys are gonna get the contract or not, but if you do, can you guys do like, it'll say the pole thickness and whatnot, and it's got a whole design spelled out. Can you like check that on the 2013 code and tell me what difference it would make?
Yeah.
That's really easy for you to do.
Yeah, that's, Steve does that a lot. I mean, that's what we're going to do is help everybody understand the changes. And we don't have those, of course, because you always run the presentation. We grab some, and this is kind of stuff we can provide
I
you.
can decide what to do with it, or?
Yeah, that's not a problem.
I'll talk brief about that because I do have one of our examples that we're going to show to you. That's a camera.
One of the other changes they had here was related to handful rims. In the previous code, you had checked the handful rim on the fatigue section on the gross properties, make sure you stayed underneath that certain allowable stress. In this check here, they've actually changed the handful rim check, and they've instituted a stress amplification factor. So when you put a handle rim in a structure, you have to check that cross section, the center of the handle rim, for the net section. So after you cut the hole, put the rim in, find your modulus elasticity, and figure out what stress you have on that. Then multiply that by 4 and make sure that number is under 16 KSI. So really your net section stress has to stay under 4 KSI to take the amplification factor out. And so at times, we're actually saying, again, that's another area that's controlling the design. So we jump into the base connection. You can get base connections higher than 4.5. We've seen in the past upwards of 10 KSI allowable stress. So a rim 18 inches up or 2 feet up at 4 KSI is going to limit the overall design of that structure. So you'll see, you get an analysis, there should be more pages, more checks, because this additional detail they put in there. And again, the stress concentration factors have been included throughout the whole fatigue design. Just something to highlight, and that's that there is no more letter designations. So 2001, 2009 had the A, B, E, E prime, D, all those kind of classifications for how much allowable stress. After 2013, there is no across the board this connection gets an E. It all depends on the actual joint configuration. They have thresholds, and they have a finite life constant. It's kind of at the bottom here is the standard, one of the standard connections to the backup ring, and depending on this factor they call KCF, which is a finite life constant, depending on what number kicks out of that equation, depends on your allowable stress. You can either find out that a connection is no good for fatigue, you can't put any stress into it, or you'll find out it's 4.5 KSI, a 7 KSI, or upwards of a 10 KSI allowable stress for a backup ring connection that we've been seeing and using for the last 12, 14 years. So the same size detailing, just depending on how big the center hole is, how big the shaft is, things like that, can have a varying allowable stress depending on this requirement.
What was the advantage of dropping the water?
The reason is, I think it's because they didn't want that one-size-fit-all approach. We can find that if you have a really thick shaft, thinner base plate, and say a pretty large center hole opening, that actual stress and the life of that structure they found with fatigue research, that will fail quicker than, let's say you had a thicker base plate for that setup, where your center hole was smaller. It's going to make that base plate stiffer and the bottom of the shaft stiffer, and it's going to give you more life. So they're incorporating that whole joint configuration and giving benefits to you having something that's a more rigid, more stiff structure and giving you higher life. It's definitely a lot more in the design.
Kevin, that's a relatively small hole in the base plate. And then we get the shops that has this big hole. And they tell us, oh, we can't do that small hole. I forget whether that's the monotubes or the...
Well, I don't, I haven't checked shop drawing for a while. Checked some lately. No, you're talking side structures, right?
It might be,
Yeah, side
yeah, I
structures.
marked it up, but that's not the standard. It says, oh, sorry, we can't.
Well, we've been sticking to it on our end. I don't know what's going on with your end there, but we've been sticking to it. And we actually developed a method for checking that handhole area. We did a little bit of finite element work, and then we turned it into a closed form solution. And we checked that, and we used that as our guide. That was a big issue in Carl Frank's research, is the size of that hole. You don't want a hole at all. That's what you want. No hole.
Yeah, you don't want it to be cut out because you
Right. So when you see the
But
size.
then it makes it dysfunctional.
Yeah, because you got this plate wanting to bend. It's like a washer,
Yep.
a big washer, and it wants to bend, and if you take too much out, it doesn't have any resistance.
And the more that bends and that base of that shaft starts.
That's right.
That's
That's
where you
basically
get the fatigue.
distortional fatigue, and distortional fatigue is the enemy.
Yep.
So we stick pretty close to what we got, and we're trying.
They put a requirement, Steve will show the equation with his examples, but the center hole, they say, can be any larger than 90% of the pole shaft diameter. So on a larger pole shaft, the holes will be coming down just to meet the maximum end of it, and it can be any smaller than 30%. And a lot of that's galvanizing some access. But I know that as we get down, we have some limits. We've gotten a lot smaller, got ourselves down a lot smaller than we had previously, but you do have concerns about the size of that center hole because In particular, if you're welding that top weld of that vacuum ring, depending on the process you put in, you have to stick your hand in a very small hole with no visual ability to see the top of that vacuum ring. The quality goes down in that weld, and then you can, and it's been shown, you can start your fatigue failure from the top of the backup ring. And so a bad weld there could be just as bad as.
And we don't weld that backup ring, we use Wyoming silicone deal.
There we go. That was the next thing to bring up. That's one thing that they've given 4 details here, and one of the ones is a vacuum ring with no weld on top, as long as you cock it after galvanizing, so you don't get some moisture trapping. And that that allows you to really bring this down, and allows you to do the same strength. So that's something to think about how you want to approach that, if that's an option or not. Steve we'll talk more about the exact equations later, but everything from bolt circles to center hole lengths to shaft diameter, all that is incorporated into the check to determine your allowable stress. Talked about this earlier, the wraparound gusset versus non-wraparound is simply life. They say you don't need to check it for fatigue, so you don't even have to worry about that as long as you're following details, either the recommended detailing in the previous chapters or other detailing that has sound engineering practice behind it.
And see, once again, if you put that on the end section, not the base section, there's no stress to compute. You know what I'm saying? This is like the end section, and it slips over a base section, and I weld to that, and you check the stress right here, there isn't any.
I think my understanding of the issues from all this came from Wyoming was you would have cracking at the edge of the gussets, which you would still have the stress there. But I think it'd be interesting to see what you have, because that would be, a great way to solve the problem.
If this slips onto something, and you're welding right here, and you compute the stress here, there isn't any on the end section. There's a stress on the base section, because this is a slip connection, right? With a moment in it. But we get rid of that stress right there. That's the trick.
Okay. We'll talk some more after. I'm interested in that. I haven't heard that before, so I'd like to see some more.
You guys, it's out of line fabrication for you, because you changed your floor scheme to do it.
Okay.
So that's why.
Yeah, trying to think back, I think it was last September and October. I think it was lowering device poles, and I think it was Valmont. I don't know, I was on vacation, I came back. Anyways, about that, what we show versus what they said they could do.
Okay.
Yeah.
Real quick, this chapter 11, or section 11, talks about all the tables in there is all set up for steel. There isn't a separate set of tables saying this is what the equations, these are your stress ranges. For aluminum, it actually just gives you a constant divided by, I think it's like 2.6. So a much lower threshold than aluminum, so really, for large structures, aluminum really is going to get quite large for fatigue, and that's the same as we've seen in the past codes. Just pointing out, they put in the commentary, they highly suggest using steel for situations with fatigue, just for sizing purposes. Chapters 12 and 13, no significant changes. That's your breakaway supports, foundation design. Those were really focuses on the provisions. So nothing really to report there. Quick summary, I think we've hit it quite well. Minimum number of sides, there's a minimum thickness of base plates and connection plates if you're designing it fatigue. New requirements for the vacuum rings. There's requirements for unreinforced holes and reinforced holes. The box rings, tinted and gusseted box connections are both acceptable. You have the mast arm connection dimension requirements, minimum of 8 anchor bolts per high mast, the overall new fatigue procedures for a high mast structure, and the no letter designation. So those are the kind of keys, big keys to remember through this. So the last bit before we move on to the next part and take a break is I just wanted to highlight and walk through their different areas they allow owner approval. The areas that with sound engineering practice you can deviate from what the code's showing, and it's perfectly acceptable. We talked about 4 of them in particular. The first one we didn't talk too much about, the stiffened tube to transverse plate connections. They had some requirements about not using radius stiffeners, but you can use them as long as there's sound engineering practice and not owner approval. The other 4, like I said, would be unreinforced hole cutouts and reinforced hole cutouts. You have different criteria that can be utilized. The mast arm to pole connections, and then the bolted connections, that's the washer, using the washer to keep the flanges or not. Those are the 5 areas in particular they called out. It can be deviated from as long as it's acceptable to everybody in the process. So with that, we actually put together a simple owner approval form. If you don't have one, if you're interested in doing a project, wanting to take some exceptions to something, to approve something else that is just good quality, you can provide a form. If you don't have something to provide us, just to document it so everybody's on the same page. With that, any comments or questions right now? We've been talking throughout, so that's great, so it might not be you, but open it up. We want to take just a 5-minute break before we go on, because next thing we'll do is we'll go on, Steve will go through 3 examples of high mass traffic and camera, and then talk vibration and some fatigue issues, and show some cool videos. Those are the best. But you want to take maybe 5 minutes real quick, stand up, stretch your legs. All right, thanks.